name is Andy Walls. I'm an IBM Fellow and the CTO for Flash Systems at IBM. I'm going to talk to you about an idea that's related to cyber resilience and the use of computational storage. To really appreciate it, I think we have to talk a little bit about the fundamentals of computational storage and one important fact. Moore's law is dead. Now, I know many of you already are angry and arguing with me. It's not dead. We're still integrating. We're still reducing circuits. We're still producing new generations of processors and things at a very good rate. All that is true. So let's not say it's dead, but it's not like it used to be. The growth rate of transistors and the reduction in lithography, it continues. However, it no longer has the growth rate that allows you to get new processors, more powerful processors, a lot more cores at the same or lower cost. Remember those days where in 2 years you could have twice the number of cores and not pay any more for the processor, or at least not pay much more. That's not true anymore. And some parts of the computing system, some parts of the server, are not keeping up to the same degree that the processor revolution has kept up, like DRAM, for example, or bus networks, or even PCI Express speeds, connectivity to peripherals. So it's certainly amazing what has happened. And let's just look at a basic server diagram. Today, it's pretty straightforward, pretty easy to get a 2-socket server to run an in-memory database, to do a lot of analytics, to run AI programs, to run deep learning, machine learning. And of course, in a basic server, you have the processors, you have a lot of memory hanging off to give you more and more bandwidth than we've ever had. You have Ethernet NICs, you have fiber channel adapters that are then connected to the cloud for the NICs to talk to other servers, as well as connected to the SAN to talk to storage arrays, or in some cases, just connected directly to NVMe SSDs inside the server. Now, there is a lot of sophisticated software and powerful processors that exist. But in today's world, what normally happens is that you go and bring all of that data that you want to analyze into this server, onto these processors, and that server, those processor cores, have to churn through all of the data, much of which is not really useful for the analytic task at hand. Let's say you want to find all of the boys and girls who bought textbooks online, all right? Well, you're going to have to bring in all of the records of everybody who bought anything, boys and girls, men and women, even old geezers like myself, and you're going to have that into your memory. You're going to look at each one of those, and most of the time you're going to say, nope, this doesn't apply. Nope, this doesn't apply. And they're taking up valuable MIPS, valuable space in memory, all right? Now, just imagine that if you used the storage array, if you had computational storage or elements, filtering elements in the storage array itself or in the SSDs that could help you sort and search and look at records, define a format, look at records, say, nope, this isn't the right one. This is one that you need, all right? And those are some fairly classic computational storage tasks that we've been talking about for quite a while. And of course, if you look at several parts of a computational storage system or just a regular storage system, you have the array itself comprising several SSDs, and in some cases, even some HDDs as well that are attached in expansion drawers. We have very intelligent NICs these days, and those NICs are DPUs essentially. And in that DPU are powerful processors like ARM processors, and they have the ability to offload the server, just like this array has very powerful processors in it, and it could also offload. And so the DPU can offload. And inside the SSD, there is spare NAND bandwidth, and it also can offload many of the tasks that could be done, that are done today inside the server. And it can offload those and in many cases have no performance impact whatsoever. Now, I'm often asked, which of these three places is computational storage really going to happen? And my response is always yes. There's a place for computational storage to occur in all three of them. It depends on what that task is. All right. In certain cases, a DPU can really offload and is the best place to put a computational storage function. In some places, the best place to put it is inside the SSD itself, because the SSD is right next to the data. One thing to consider in a storage array is the fact that today, getting 100 gigabytes per second is still difficult. It's possible there are arrays out there, like my own, that can achieve 100 gigabytes per second. And of course, that's if the switches, the CPUs, and the network itself allows for that kind of traffic, considering everything else that is going on. Now, inside that array, there may be 168 gigabytes per second, maybe even 200 gigabytes per second of SSD bandwidth. So you can see much of that bandwidth is not even used even in very strenuous applications by the host. So there's additional bandwidth that could be used to analyze data, to filter data, to do searches. There's bandwidth available. Now let's look at the NAND flash itself. If you were to take that array and inside all of the SSDs, there's about 768 gigabytes per second of potential bandwidth off that NAND flash. Now, some of that bandwidth is used for garbage collection at times. Some of that bandwidth is reserved for rebuild operations, for other things. But there is a lot of additional bandwidth that's not used today. So why not use that bandwidth for additional offloads, for additional functions that we can really put next to the data, instead of having to pull all the data over the network onto the server and use those valuable, those expensive processors to do that, in addition to the mainline analytics that we need them to be focusing on, right? Now, if we dig into that SSD, if we look closely at it, there's some potential inside that SSD that I believe can really help in our mission to have cyber resilience that is up to the job, that is able to handle the threats that we are exposed to in this day and age. All right. So what is it about them that is special? Well, an SSD has visibility to all the data flowing into that system, and it can do things like compress and encrypt that data with no performance penalty whatsoever. None. The data can come in, and with a very fast compressor, the data can be compressed essentially with no delay. Okay, maybe 5-6 microseconds, but it's not even visible. It can encrypt with no performance penalty. It can also perform some other checks on that data with no performance penalty whatsoever. We're going to talk about some of those checks that it can do in just a moment. It has intimate knowledge of the access patterns. It obviously knows the reads that are going on, the writes that are going on, how big those operations are. Is it an 8K read? Is it a 64K read? It can keep track of, was there a read just before there was a write to the same LBA? It knows the latency. It knows the type of data transfer. It knows how many IOPS. It knows when things were done in relationship to each other better than any other part of the system. In fact, additional information can be passed to the SSD about the volume identifier, which file this is part of, all kinds of information that then the SSD can use in association with these other things that I mentioned to really analyze and know if certain things are being done. It can figure out trends and it can make predictions in a very intelligent manner, which leads us to this. When one considers all of that I just talked about, all right, when you look at what the SSD knows or can know and what it can do, although the SSD is missing context that other parts of the system may have, like it doesn't know who's accessing it, it's not a file system, it may not know exactly parts about the application, but it can generate data needed for determining ransomware attacks with less performance impact than any other part of that system. All right. The it it can, without hurting performance, it can tell if compression is starting to change. In fact, an SSD can know if compression has changed from one IOP that happened to another if it's designed correctly. It has the potential for determining or helping to determine more rapidly that there is a ransomware attack. So that makes for a very interesting computational storage application indeed, and one that is not just important for the storage industry, but one that's important for society. We need to do all we can to combat this attack on our infrastructure and our data. So there's a second realization. Now, to be truly effective in detecting ransomware as early as possible, it requires coordination between all parts of the system, all parts of the stack. A lot has been done in sophisticated security software to keep out attackers, to look at logs to see if people without authorization have gotten in, and to try to keep the bad guys out and to raise alerts. And it's extremely useful, and that industry is making great strides. But we need to look at what we can do at every single part of that stack. And when I look at SSDs, when I look at storage, I see it also is unique in what it can do. And, and it also can help in the early detection of malware, especially when that malware involves the data. Obviously, an SSD is not going to know in and of itself if an attacker has gotten access to a password, a weak password, and started to infiltrate the system. That's not something that an SSD can do. But as that attacker starts to change the data, starts to encrypt the data, starts to delete the data, there are things that the SSD can keep track of that can help, especially in conjunction with other things in the system. So the type of malware that an SSD can be useful against is ransomware. In ransomware, the data or part of the data, some of the data is encrypted in such a way that it supposedly can be unencrypted if you pay a ransom for it. Another type of very dangerous malware is what we call wiperware. Just the criminal just wants to delete the data, wants to destroy the data. Now, in addition to these activities that are malicious, that are premeditated, there's also a lot of mistakes that happen. I've talked to clients before and excellent administrators who recount to me the time I deleted a file by mistake. I deleted a volume by mistake. And so these could also be detected by the SSD. Turning encryption or compression on in an application. This is something that an application owner may do without the administrator knowing. And it's not malicious, it's not a mistake. However, it needs to be understood rather quickly that the data reduction is decreasing so that the storage administrator can understand that he might need to bring in more storage since the data reduction is going to decrease. There's another area that is extremely hard to detect. And we're going to have to wait and see if SSDs can help significantly here. But I think we can. And this is the area of exfiltration. Exfiltration is stealing data. It is extracting the data, but not hurting it. And then by stealing that data, the thief can sell it, can do destructive things, and exfiltration is very hard to detect. But I think when you look at what SSDs can do and how they could do it, what could be kept track of, what could we offload, and how would that help in the mission of doing the things that I just mentioned, helping to know when one of those activities is occurring. First of all, intelligent SSDs in this way, they can be given additional volume awareness. We've talked about this before in the industry, giving access to the volume, to which file it's part of, what is the OS, what is the application that's running, what is the hypervisor that's running, and understand the mapping between the LBAs on the SSD and the volume and the file. Where is the directory for the file system, for example, and helping to know where a given LBA resides and what it's part of. Now, hints can also be passed on the type of data access in a storage system, in an SSD, in an environment where applications are being run. Sometimes there are things that should be ignored that are not part of an application that could in fact give false positives if they're not considered. For example, an OS or a storage array is going to do what we call scrubs, where it goes out and looks at all the data, reads it, checks the parity stripes perhaps in RAID, make sure the parity is consistent. Well, that's something that you want to ignore when keeping statistics about host accesses. Otherwise, it might look like something's going on when it's really not. And this could be also true for rebuilds in an environment where an SSD has failed, and many other cases that you want to pass hints so that that data is not being examined and being kept track of. Now, the other exciting thing that an SSD can do is to check for randomness and data transformation on the fly. Things like compressibility that we talked about can be checked on the fly to see if that compressibility has changed. Now, there are many other measures of randomness that are used to determine if encryption has been turned on and to help tell the difference between encryption and compressed data above, encryption, and maybe media files and other things. It's a sophisticated area that's being researched all the time, but these checks could be done, they're mathematical checks that could be done on the fly by the SSD as the data is coming in, and in fact compared to previous results. Trends can be recorded. Various data attributes can be identified. And extremely important is that key access attributes can be recorded and changes can be identified. For example, the fact that reads are happening before writes, or that it looks like somebody's reading through all of this volume in order, and that hasn't been done before, or that reads are happening at a higher rate than they were being done. And all of these things can be kept tracked up and then compared to normal activity or compared to known ransomware, and therefore give information to machine learning models to help identify this corruption early, and combine that with other parts of the system and information that's known to give a good solid view as to whether ransomware or wiperware or just innocent things are happening, right? So what are the benefits and some important notes when considering this important offload? Well, early discovery is everything. And by putting some of this ransomware detection, early ransomware detection capability into the SSD and not impacting performance, it can help to reduce that window of corruption. It's not going to be possible to determine that ransomware has occurred in the very first access by looking into an SSD. You need some history, but perhaps we can reduce that window down to a few minutes, or even maybe tens of seconds, maybe even less. And that then speeds up the recovery. It helps to be able to identify and go back to a known good snapshot or backup and reduce how much data was impacted and allow the individual to recover without having to pay that ransom. It's not sufficient in itself. It has to be combined with other security and cyber resilience protection capabilities that are available and being developed. So, in conclusion, computational storage has a lot of potential as servers become, let's say, not less powerful, not as the speed, but as the speed of invention reduces somewhat. As Moore's law slows down, we have to distribute the load among all parts of the system, including the storage. Today it's used to store, but there's capability to do additional things. And I can't think of anything more important and really more geared toward SSD and storage than the ability to look at that data, to understand, to analyze it, and to be able to recognize patterns that could identify a corruption of some extent, whether it's malicious or accidental. So this whole area of ransomware detection, I think, is ripe for innovation with computational storage. Thank you very much.